Welcome everyone to session 5 in this webinar series. So today's focus is on multivariate autoregressive data. You can also call it multivariate time series. So essentially it's the data is autoregressive. That means it has strong autocorrelation and also it has strong cross correlation with other data sets. So one example of that might be a collection of sensor data. So out of all the four, so we in the very first session we talked about 4 different categories along 2 dimensions, and the 2 dimensions were whether the data is univariate or multivariate, or whether the data is has autoregressive properties or not. So out of those 4, this is by far the most complex to deal with. So most of the good solutions are based on are fairly recent, and they are mostly based on deep learning. So our focus will be on deep learning based solutions, although there are other classical solutions available, but we won't be covering those. So, and if you look at the deep learning solutions, so we'll be reviewing about 8 or 10 papers in this session. So these solutions typically has a pattern. The pattern is there is a recurrent network of some sort which models the temporal correlation, and there is some sort of so that's one component of the solution, and the other component is either an autoencoder or a generative adversarial network, so GAN, which captures the spatial correlation. Just like the RNN captures the temporal correlation, this other component captures the spatial correlation. So together, they give you the complete solution for multivariate time series data anomaly detection. So all the solutions are based on a sliding window. So let's say you have your data set has 10 different signals, and then you have a time series of t. So essentially, if you look at a window worth of data, it's like a 2D data set. We'll do a quick overview of the various deep learning networks that are used in these solutions. So it's a very quick overview. So obviously, if you are interested in more details and want to have a more thorough understanding, you have to refer to other online resources. So this is a very quick, 1 paragraph per item kind of description. So recurrent neural networks, they're RNN, they're used for modeling time series or any sequential data. So by sequential data, I mean where the order of the data matters. So time series is the most common example of that, but it doesn't have to be time-based. So in RNN, there is the hidden unit takes the actual input as well as the output of the hidden unit from the previous time step. So that's how it captures the temporal relationships. Long-term, short-term memory, it's a kind of RNN, which is more, and it's more sophisticated. So one of the problem with the basic RNN is that it doesn't work very well for capturing long-term memory based correlations. And LSTM overcomes that issue. So instead of a hidden unit, LSTM has almost like a subnetwork, and there are 3 gates in that subnetwork to control the input, the output, and the cell content. So for example, the forget gate controls how much of the past information should be retained in the current timestamp. So this is how it controls how much from the past memory it should retain. So you can control that. Gated recurrent unit is also similar to LSTM. It's a little bit simpler than LSTM. It has two gates, update and reset. The update controls how much of the past information should be retained, and reset controls how much of the past information should be forgotten. Autoencoder is a network that tries to replicate the input. So the input goes into the encoder, which encodes the input to a lower dimensional latent vector space. And then the decoder takes that and tries to recreate the original input. And so the error is based on the the reconstructed input and the actual input, and that's how the network gets trained. Its purpose is similar to PCA for dimension reduction, except that autoencoders are more powerful because unlike PCA, autoencoders can be nonlinear. Variational autoencoder, you can think of that as like a probabilistic version of regular encoder. The encoder output, instead of being a set of discrete values in the latent space, it's actually a probability distribution parameters of the latent space, variables. So for example, if it's for Gaussian, it's mean and standard deviation. And then the decoder samples that probability distribution and then tries to regenerate the original sample. So VAEs are more powerful because it has a smoother representation in the latent space. And the output of the VAE can be the actual regenerated input, or it could be the parameters of a probability distribution for regenerated input. So it could be either one of the two. GAN, generative adversarial network, is a very sophisticated, complex network. If you are aware about, for example, deepfakes, so this is the underlying technology behind that. And it's very unique the way it works. So its goal is to learn whether some data set is real or fake. So GAN has two subnetworks. One is called the discriminator and the other is generator. So the discriminator is like a regular feed-forward network for classifying. And it classifies between real and fake data. So for example, the discriminator might will take real data, and then it should be able to predict that it's real data, not fake. What the generator does is that it takes data from some distribution and generates realistic looking fake data, and it tries to get the discriminator to classify the fake data as real. So as you can see, the two subnetworks, they're kind of pitted against each other. It's like a two-player game essentially. So the discriminator is always trying to classify real as real and fake as fake, while the generator will try to get the discriminator to make the wrong classification, or in other words, fake as real. Convolution neural network, although this is not used much in the time series data, but there is one solution that's based on convolution neural networks. So you can use convolution neural networks for time series also. But its main use is for 2D data, like image classification and object detection, that kind of use cases. So the way it works is that you define a filter, and then the filter slides over your data, and then as it slides, you perform a convolution operation, which is essentially element-wise multiplication followed by addition. The convolution result goes through a nonlinear activation and then something called pooling, and then you can have as many filters as you want. And as the network gets trained, the filter weights are learned. So that's how CNN works. Like I was saying before, a very common use case for this kind of data, multivariate time series is collection of, sensor data, which are related to each other. It could be manufacturing or, automotive, the various domains, medical. The first two solutions are kind of cheating. So, for example, what you can do is, so with this kind of data, we are dealing with two kinds of correlation. One is temporal, the other is spatial. So what you can do is you can eliminate the spatial correlation with an autoencoder. So you run your multivariate time series to an autoencoder. Let's say you had originally, let's say you had 10 data streams. Let's say you got that down to 4. So now you have 4 different time series, but they're in a different space, in a different dimensional space. And then each one of those will be independent of each other. So because by running it through the autoencoder, you are able to get rid of the spatial correlation. So once you have done that, then you can take each one of them as a univariate time series and apply any univariate time series algorithm. So that's how that works. This one is you do something similar, except that you try to remove the temporal correlation first. For example, if your data is time series with seasonal or trend, then you can use some algorithm that will separate out the different components, like the seasonality trend and the random residue component. So for example, HTL is one way of doing that. But there are other tools also. For example, Facebook has something called Prophet for time series forecasting. It will also do the same thing. So once you have the residue component, then you're dealing with just a multivariate data set. You're not concerned about the temporal correlation anymore, because you have removed the cycle and the trend. So once you have done that, so then you can treat that as a multivariate data set and use any algorithm that works for multivariate data set. So for example, you can use autoencoder, or you can use isolation forest, which we covered in the last session. So from here onwards, we are going to go through real deep learning solutions for this problem. So this one is based on GRU and variational autoencoder. So the GRU takes care of the temporal relationship, and the VAE takes care of the spatial correlation. So what happens is so the GRE output goes to the VAE and goes to the encoder, and then on the other end, the encoder output goes to another GRU, and then you reconstruct the original data. For this solution, they also do something which is a little bit different from regular VAE, which is to concatenate the encoder output of the previous timestamp. Concatenate the GRE output with the previous timestamp encoder output. The decoder output is the probability distribution parameters of the reconstructed data. So once you have that, the way you find out your anomaly score is that with respect to that distribution, you find out the probability of some given test data sample. Okay. And then your anomaly score will be related to that probability. Lower the probability, higher the score. But they actually go, so that's what will give you the anomaly score. Also in this solution, they use for anomaly score threshold, they use a technique based on extreme value statistics. So I won't go into the details, but you can, look into the paper if you're interested. So it's basically GRU and VAE. And like I was telling you before, the VAE output can be the actual discrete values for the reconstructed data, or it could be parameters of distribution for the original data. So for example, if it's a Gaussian distribution, then let's say your input data dimension was 10, your output will have 20 elements because you will have mean and standard deviation for each dimension. So that's that. The next one is, it's based on LSTM only. It doesn't use any other network. So what it does, this is the simplest possible solution with deep learning for this kind of problem. So all you do is you use LSTM, and in this case they happen to use 2-layer LSTM. Then you use the LSTM to forecast. So for example, if you define your window size to be 10, then for each 10 time steps, you forecast the 11th time step. And then your anomaly score will be based on the error, the difference between the forecasted value and the actual value. So this is the simplest possible solution for this kind of problem using deep learning. It uses only LSTM. There is no autoencoder or GAN involved. And the other thing is, with this one, you can either do point anomaly or sequence anomaly. So if you forecast over a horizon, then you will get a sequence anomaly. But if you forecast only the next timestamp, you will get the point anomaly. Now, for all other solutions that I have listed here, for rest of them, you'll only get sequence anomaly. You cannot get any point anomaly. This one is LSTM along with autoencoder. So you have, so the autoencoder has encoder and decoder, and the encoder and decoder, they are both built on top, on top of LSTM network. So what happens is, so the decoder output will be the regenerated subsequence of the time series. Now this time series is multidimensional, so it will be multidimensional reconstructed the time series sequence. And the error, what they do in this solution, they take the error and they feed a normal distribution to it, and then the anomaly score is based on the z-score of the distribution, of that error distribution. So the error is the difference between the reconstructed data and the original data. So it's LSTM and autoencoder. The next one is LSTM and variational autoencoder. So that's the combination they're using for the next one. So like I was saying before, the VAE will output the probability distribution of the reconstructed data. And the decoder output is the parameters of the, the encoder output is the probability distribution in the latent space, and the decoder output is the probability distribution of the reconstructed data. And like the previous solution, the encoder decoder is also based on LSTM network. So the difference is in this one, they use regular autoencoder, and this one is BAE. So again, the anomaly score will be tied to the probability distribution of the reconstructed data. So if it's got low probability, the anomaly score is high, and vice versa. This is the only solution that uses CNN. So like I was saying, although CNN is meant for 2D, but we do have 2D data, because when you have multi-dimensional time series and you're taking a window, you essentially, each window is essentially 2D data. So on that 2D data, you can have a CNN and you can do convolution operations. And that's what they do here. So again, with the CNN, they do forecasting, and the anomaly score is related to the forecast error. So this is similar to a simple LSTM based solution that we looked at earlier. I think it's yeah, I think it's this one. See, this one is LSTM only. So this solution is similar, except that instead of LSTM, it uses CNN. But it's otherwise it's very similar. The solutions we have from onwards, going from this solution onwards, they all have GAN as part of the solution. You see, all of them has GAN. So GAN, again, a quick overview. GAN has two components. There is a discriminator and then there is a generator. And the goal of the discriminator is to predict whether some data set is real or fake. And the goal of the generator is to generate fake data and try to fool the discriminator. So what happens is, as the network gets, and the way the training works for GAN is it's trained alternately. So in one cycle, with one batch, you'll train the discriminator, and then for the next batch, you'll freeze the discriminator and you'll train the generator, and back and forth. So that's how the training, you train GAN. So as the training progresses, the data generated by the generator will look more and more realistic. So a generator is successful when the discriminator is not, that's actually interesting. You have a good GAN network when the discriminator accuracy is low, because that means that the generator has been able to fool the discriminator. So the first one uses GAN. Now GAN also has two networks, right? The discriminator and the generator. So since we're dealing with time series, they'll require some sort of RNN. So for both the discriminator and the generator, LSTM is used. And for this kind of network architecture, the anomaly score is related to the weighted sum of the generator error and the discriminator error, because each one will have some error, right? So for example, if the generator has generated the data and the discriminator is catching it as an error, as fake data, the generator will have high error. So the anomaly score will be related to the weighted sum of generator error and the discriminator error. For testing with to predict anomaly detection. So these generators typically they take data from some given distribution, random distribution, and then as the data flows through the generator network, it changes to realistic looking data. But what they do here for testing purpose, they, instead of taking some random distribution, they train another network to generate the data and then take the error, the difference between the generated data and the real data to kind of map the real data to the to the random distribution data in a better way. Let's see. So this one also uses GAN. It uses LSTM for the generator and convolution for the discriminator. That's interesting. To match data with the features in the latent space, it also trains another network called encoding network. And to correctly map into the latent distribution, a second discriminator network is also added. So this solution is fairly complex. It involves 4 different subnetworks. And for, like we saw in the previous GAN solution, the anomaly score is related to the discriminator error, some sort of summation of the discriminator error and the generator error. So for the generator error, typically you do like a mean square error, or you take some sort of point-wise difference and sum them up. But in this solution, they, instead of doing that, they suggest using a technique called dynamic time warp. So that's a time series algorithm for finding similarities between 2 different time series, or the difference in area under the original and the reconstructed data. So for the reconstruction error, they propose slightly different techniques. And for anomaly score, also their solution is a little bit more complex. What they do is they take the reconstruction error and the discriminator error, and for each one of them, they fit a normal distribution and takes the z-score from the 2 distributions. And then they do a element-wise multiplication on the two z-scores, and they claim that it works better. So this solution is fairly complex. There are 4 different subnetworks involved, and if you look at the paper, if you look at all the loss functions and all that, it's pretty complex. It's not. It's a. It's taking the basic GAN and then extending it by adding 2 more subnetworks. So PAEGAN. So this is GAN, and again variational autoencoder. So what they do here, this is also interesting. Now so what happens in a GAN? So if you look at the generator for the GAN, the input to the generator is data from some distribution, and then the network gets trained to transform the data to realistic looking data, actual data. So what they do in this solution is that they use a slightly different generator. They actually use a VAE for the generator. And the advantage of that is that, so the VAE input is actual data. And then the VAE output will be some distribution in some latent space. So if you look at this solution, the decoder for the VAE, that's kind of comparable to the generator for a regular GAN, except that here the distribution is based on actual data, because the VAE encoder input is the real data, and that real data gets transformed into some distribution in a lower dimensional space. So it's better than the regular GAN. So again, to sum up, it's like a GAN, except that the generator network of the GAN has been replaced with the VAE. So that's one way to describe it. Again, the anomaly score is related to the weighted average of the generator and the discriminator. So, so those are all the solutions. And today's session, we won't have any demo because it's not trivial to implement some of the solutions. I mean, it can be done, but it takes time and resource. So I don't have any demo. I guess there could have been a demo based on very simple solution like LSM only, which you can easily do using PyTorch or TensorFlow. So for example, this one. No, I'm sorry, this one. Yeah. So this one uses LSTM only. It's fairly simple. It can easily be implemented. So to kind of summarize, so the deep learning based solutions has the two categories. Either, first of all, there always has to be a RNN network, which could be the regular RNN is never used because it's not powerful enough. It cannot handle long distance memories, things that are too far in the past. It's either LSTM or GRU. Most of the solutions, as we saw, it uses LSTM or GRU for modeling temporal relationship, and then either a autoencoder or VAE or GAN to handle the spatial correlation. So most of the solution will give you a sequence anomaly. For example, if your input is a window of multivariate time series data, it'll tell you whether that whole window is anomalous or not. But if you look at the simple LSTM based solutions, they can give you either point anomaly or sequence anomaly. It depends on how much you're forecasting. If you're forecasting only one step ahead, you will get point anomaly. If you're forecasting like n steps ahead, then you will get sequence anomaly where the sequence length is n. So that's kind of the summary. So obviously, there are a lot of details involved. So for example, let me just show you one paper. No, sorry. Yeah. Just give me one second. I wanted to show you, just to kind of give you an idea about the complexity of the solution. Let me show you one of the GAN-based solutions. Just 1 second. Actually, I have so many windows open. Yeah, I think this is a good one. This is the one I was telling you about. I think it's fairly complex. So this is this one, MAD-GAN, which is sorry. Yeah, this one. So GAN, LSTM. Yeah, so this is not the most complex one, but this is a good one to look at. So if you look at the network architecture for this one, so this is training. By the way, all these solutions are what's called semi-supervised algorithms, because for all of them, you have to build a model using normal data. And that's why it's semi-supervised, because you're only modeling the normal data. But if you had data that's labeled normal as well as anomaly, that's fully supervised, which is very rare for anomaly detection. It's either semi-supervised or unsupervised. So this is the the training part, where they train. This is the discriminator and this is the generator. They're both based on LSTM. This is the input, and then this is the the testing part. And here, they show you some of the GAN uses something called min-max loss for training the network. So that's this here, min-max. And this is how this is a complete algorithm. See, this is how they combine right here. They combine the reconstruction error and the discriminator error, or the generator error and the discriminator error. They combine with as a weighted sum, and that's your anomaly score. And here are the data sets that we used and the examples. So this one is let's see, from 2019, so fairly recent. From University of California, Berkeley, and then National University of Singapore. Okay, let's go back to, I just wanted to show you one paper as an example. So that's all I have for today. There's no, like I said, there's no demo because I didn't implement any solution. So I just wanted to focus on the algorithms and the research papers and show you the direction in which it's going for solving this kind of problem. So this is kind of like a survey of different solutions that are available out there. So I'll stop there and we'll see if there is any question or anything. question.
Yeah, there's one question from Richard. It says, he says, what is the link to the materials? Can you please share the link to the materials?
Okay. Yeah. So by the way, Sharon, actually, I'm able to see the QA myself today because
okay.
I missed it. Yeah. So I'm actually looking at it. Link to the material, the Google Doc. The Google Doc will be available. As far as the different papers, I didn't provide the link for those, but I think the best way to find them is if you do a search on Google with the whole title, it'll come up. If you want to read the original papers, but I didn't provide the links to the original paper in the Google Doc, just the complete title. Okay, anything else? No. Okay, Sharon?
Yes, Pranab. If any of you have any questions, I think there's another one there.
Yeah, I'm looking at it. Are we going to find the titles to the paper on your Google Doc? Yes. So for example, yeah, I mean, so this is the title, LSTM-based PAEGAN for time series anomaly detection. It's the actual title, verbatim. It's not paraphrased. So you can just type that in Google and you'll get hold of the paper. Okay. Yeah. The bullet points, some of the aspects are really useful. Yeah, I agree, but it's a lot of hard work, preparing those bullet points to at least understand, absorb, most of the paper before I could summarize in bullet points. It took a lot of time, but I'm glad it's useful.
If there are any more questions, you can make use of the Q&A.
Yeah. One more point.
Yes.
Would you be willing to go through an implementation session of one of the papers? Yeah, I will. Yeah, I might work on one of those and then do a session on just an implementation. I could do that. I mean, the one based on plain LSTM, that can be done pretty easily because that shouldn't take more than a few hours. But anything that involves, the VAE and LSTM, it'll be more complex. If it includes GAN, that's the most complex. So yeah, I'm open for that. I'll see, which solution makes sense for implementation. Yeah, I'll keep that in mind.
Thank you. Yes, we just have a few more minutes left. If you have any other questions or any queries regarding the learning series itself, you can use the Q&A window.
Yeah, I don't think we have any more.
Yeah. All right. Yes, I think, should we wrap this up, Pranav?
Sure.
Yep. So the next session will be on 18th December, and it will be session number 6, data long-term drift or change point detection on Spark and Scala. So that will be on the 18th of December. And we will, as usual, we will be sharing the class recording as well as the class notes shortly. So I think that's it from us. Thank you all so much. And thank you, Pranav, for your valuable time.
Sure. Thank you, everyone, for joining. Hope to see you again. soon.
Yeah, thank you. Yeah.